The secret history of transformers. 1,000 years we've kept it hidden to protect Earth from what was destined to arrive.
Wait, no, where's my bumblebee?
The transformer are commonly used in applications where there is a need of AC voltage conversions from one voltage level to another.
It is possible either to increase or decrease the voltage and current by the use of transformer in AC circuits based on the requirements of the electrical equipment. For various applications, a wide variety of transformers are used, including power, instrumentation, and pulse transformers.
In abroad, transformers are categorized into two types, namely electronic transformers and power transformers. Electronic transformers operate voltages that are very low and are rated at low power levels.
These are used in consumer electronic equipment like televisions, computers, radios, and other devices, whereas the term power transformer is referred to the transformers with high power and voltage ratings.
These are extensively used in power generation, transmission, distribution, and utility systems to increase or decrease the voltage levels. However, the operations involving in these two types of transformers are the same. So let us go in detail about transformers.
Transformers, also commonly known as voltage transformers. They were invented by the famous scientist Nikola Tesla. Transformers are commonly found in our household as they are present in a variety of devices around our home. A transformer works based on the principle of Faraday's law, as Faraday's law states that when the magnetic flux linking a circuit changes, an electromotive force is induced in the circuit proportional to the rate of change of the flux linkage. The current from the electrical supply, as you can see here, is actually an alternating current. Alternating current from the power supply supplies a magnetic flux or changing magnetic field lines, which is shown by the red markings here. They are in the soft iron core. The changing magnetic flux produces an induced E.M.F. across the secondary coil, which as a result the secondary output voltage is also an alternating voltage. Transformers are capable of either increasing or decreasing the voltage and current levels of their supply, without modifying its frequency or the amount of electrical power being transferred. In this diagram, we can see an example of a step-down transformer, as the secondary windings has less windings than the primary winding.
A single-phase voltage transformer basically consists of two electrical coils of wire, one called primary coil and the other secondary coil. The primary side of the transformer is the side that usually takes power, as you can see here. And the secondary is the side that usually delivers power. The supply voltage is called primary voltage, also known as input voltage, while the voltage across secondary coil is called secondary voltage, output voltage. In a step-up transformer, the secondary coil has more number of turns, while in a step-down transformer, the primary coil has more number of turns. Assuming this is an ideal transformer, we can apply the transformer turns ratio where Np divided by Ns equals to Vp divided by Vs. The two coils are not in electrical contact with each other, but are instead wrapped together around a common iron core to allow electric current to flow through. This soft iron core is not solid but are made up of individual laminations of iron connected together to help reduce energy losses such as eddy current. When an electric current passes through the primary coil, a magnetic field is developed which induces a voltage into secondary coil.
So what actually is back E.M.F? It is an induced voltage or E.M.F that pushes against the current which induces it. Basically, it is the E.M.F induced in a circuit based on two physics laws, which is the Faraday's law and Lenz's law. In order to really understand about how back E.M.F is induced in a transformer, you really need to understand the definition of both laws. First, Faraday's law states that the changing magnetic flux linkage in a circuit produces an induced E.M.F which is directly proportional to the rate of change of magnetic flux. Next, Lenz's law. The direction of the induced E.M.F is such that it opposes the change in current that produces the changing magnetic field which induces it. Basically, the induced EMF will oppose the original EMF, which led it to be induced.
Now, I'm going to explain about back EMF in a transformer. Firstly, alternating current flows through the primary coil, and this will produce changing magnetic flux. And this changing magnetic flux links in both coils. Hence, based on Faraday's law, it will produce an induced EMF in each coil, which is the primary coil and the secondary coil. Now, in the primary coil, the direction of the induced EMF opposes the supplied voltage, Vs, and the change in current, which is based on Lenz's law. This induced EMF is what you call back EMF. So I'll put it in blue, VB1, back EMF. And due to this back EMF, the net voltage, Vnet, equals to Vs minus VB1, which is very small. Why it's very small is because back EMF 1 is almost the same as voltage supplied. Now, for the secondary coil, the induced EMF, which is written as V2, it will be in the same direction as the back EMF in the primary coil. This is because both of them will be induced by the same changing magnetic flux in between the coils. Next, secondary EMF will cause an AC current to flow through the secondary coils. This secondary EMF causes AC current flow through the secondary coils. This AC current also produces changing magnetic flux, which links to the primary coil. Hence, it produces another back EMF, VB2, in the primary coil. I'll put it in blue. This back EMF opposes back EMF 1, but it points in the same direction as supplied voltage. Why? It's because back EMF 2 will oppose the secondary EMF in secondary coil, which causes changing magnetic flux, which causes it to be induced. Hence, the new equation is given by Vnet equals to same equation, but added with VB2, which will be very large. Here are some energy issues in the transformers. It may be due to the resistance of windings. The primary and secondary coils are made of copper wires which have low resistance. Therefore, there are some energy loss in the form of heat in the coils. And as you can see here in this picture of transformer, this part here is the windings of coils in the transformers. The question you all may ask is, why do we use copper? If we take copper compared with aluminium, it has lower specific electrical resistivity, and its current distribution is more uniform because it has a higher conductivity, and it also has a higher tensile strength. What is tensile strength? Tensile strength is the amount of tensile stress it can take before breaking. Okay, copper loss is due to ohmic resistance. And what is ohmic resistance? It is also the electric resistance, or you may also call it impedance, of the transformer windings. This copper loss of the primary winding is I square R, which I square R is actually the formula of power. And here you can see the total copper loss will be power of the copper equals to the primary windings and secondary windings power loss add up together. So to conclude that, it is clear that the copper loss is proportional to the square of the current, and current depends on the load. So copper loss in the transformer varies with the load.
Besides that, a common factor of energy issue in a transformer is magnetic flux leakage. This happens when magnetic flux cannot pass through the ion core effectively, thus causing the magnetic flux to complete the path in air. Besides that, the leakage of magnetic flux only happens in the ion core, which can be seen here. Due to this leakage flux in the transformer, there will be a self-reactance in the concerned winding. This self-reactance associated with resistance of transformer is impedance. Due to this, there will be voltage drops in both primary and secondary transformer windings.
Besides that, there is eddy current, which causes energy loss. The changing magnetic field in the core of the transformer not only induces current in the secondary coil, but also currents in the iron core itself. These currents, which flow in little circles in the iron core, are called eddy currents. According to Lenz's law, the current swirls in such a way as to create a magnetic field opposing the change. To do this in a conductor, electron swirls in a plane perpendicular to the magnetic field. Because of the tendency of eddy currents to oppose, eddy currents cause energy to be lost. In other words, eddy currents transform more useful forms of energy, such as kinetic energy, into heat. That is generally much less useful. In many applications, the loss of useful energy is not particularly desirable.
Hysteresis. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The repeating core magnetization process expands energy, and this energy appears as heat. The heat generated can be kept to a minimum by using a magnetic material which has a low hysteresis loss. As you can see in the first graph, the larger the magnetization and higher the heat, this is more desirable to act as a permanent magnet or a magnetic recording. Whereas in the third graph, we can see that it has a larger magnetization but a lower heat. Therefore, this is more likely to be a transformer. Hence, soft iron is often chosen for the core material because the magnetic domains within it changes rapidly with low energy loss.
Now that we know how the transformers work, how should we make use of it? Transformers can be used in the transmission of electricity over long distances through the national grid network. It's a high voltage electric power transmission network connecting electrical power stations to consumers like you and me. Electrical energy generated in power stations have a voltage of 25 kilovolts. From there, it goes through a step-up transformer, which increases the voltage to 132 kilovolts, before being transmitted over long distances through the national grid. This is done to reduce power loss in cables. Heat is generated in cables due to electrical current. Therefore, to minimize this power loss, the current is reduced. Based on the equation P equals to IV, when V is increased, I could be reduced, which helps to reduce power loss. The reduction in power loss will help to reduce costs and enable electrical power to be transmitted more efficiently. This voltage is subsequently reduced by substation step-down transformers to suitable voltages for consumers. For instance, in heavy industries, they use 33 kilovolts, while light industries use 11 kilovolts, and for normal residential areas, it's just 240 volts.
Hi everyone, today I will be talking about the other application of transformers. Based on the operation of coils, there are many different types of transformers in the market. They all serve a common set of purpose in regulating electric current. First off, I will start with the electronic device charger. For example, our handphone chargers. The concept of charging is fueled by the functioning of generators. Transformers are used to control the voltage that enters the battery during charging process. This is to prevent damages that can occur into the internal battery components. This is very important because unregulated voltage can result in high damage during charging. The other application of transformer is the stopping and starting the flow of electricity. Transformers are also useful in stopping the flow of electricity and interrupting electric current. Transformers are commonly present in circuit breakers where we utilize a switch automatically to interrupt the flow of electricity. For an example, we have the switch that we use in the household. This is to prevent damage that can occur as a result of high voltage. Next up is steel manufacturing. Steel manufacturing is another use of transformer. Steel manufacturing plants rely on the functioning of high voltage for the manufacturing process. High current are required during melting and welding process, whereas low current is needed during cooling process. Hence, transformers are necessary for regulating current within the circuit.
Professor, why do we need to modify a transformer?
The purpose of modifying a transformer is to reduce the cost and increase its efficiency as much as possible.
As mentioned previously, energy can be lost through heating effect of current in a coil. How do we improve that?
We know that power is lost as heat I squared R, whereby I is the current flowing through the coil and R is the resistance of the coil. We can simply use thicker copper wires of low resistance to reduce the heating effect of current in a coil. Coolants used in a transformer are oil and air to decrease the temperature of the transformer. The coolant circulating inside the transformer transfer the heat from the winding and the core entirely to the tank walls, and then it is dissipated to the surrounding air by radiation and convection.
How about the heating effect of induced eddy currents?
A laminated iron core is used whereby each layer is insulated with enamel pan to prevent the flow of eddy currents. The high resistance between layers of the iron core decrease the prevalence of eddy currents and heat.
But there's still problem with flux leakage. How can we solve that?
Some of the induced magnetic flux from the primary coil is not transmitted to the secondary coil. Therefore, the E.M.F in the secondary coil is decreased. The secondary coil are intertwined tightly with the primary coil. The iron core should form a closed loop. It is one of the methods to
increase the efficiency.
Other than that, the energy used in the magnetization and demagnetization of the iron core each time current changes its direction is known as hysteresis. This energy is lost as heat, which subsequently heats up the iron core. We can improve this by using a soft iron core that is easily magnetized and demagnetized, such as mu number.
Thank you for watching our video. I hope you have a better understanding of transformers now. Bye!
Yes. 3, 2, 1, shut up. No, continue. Okay, 3, 2, 1. No, continue.